come back. Okay, let's come back to the video. Okay. I guess you can see this now. Right? Hello?
No.
Can you see this?
Okay, yes, I can see it.
All right, no problem. Let's continue.
I can see it.
Okay.
These principles.
Yes, sir.
Why do we weigh less in water? Hey, looks like you have gained a lot of weight. Come on, let us check your weight. You weigh 132 pounds. All right, don't get stressed. Check your weight in water. Oh, look, it is much lesser. Do you know why you weighed less in water? The answer to this is based on Archimedes Principle. Not that principle. Oh. Archimedes' principle is a fundamental truth which states that an object fully or partly immersed in a fluid experiences an upward force called buoyant force, which is equal to the weight of the fluid displaced by it. It went over your head, right? No worries. Let me explain. Gravity pulls us downwards. Hence, the weight of our body always acts downwards, whether we are on ground or in water. However, according to Archimedes' principle, when we are in water, we experience an upward force. That is, buoyant force, which is equal to the weight of water displaced by us. This upward force cancels a portion of our weight, causing us to weigh less in water.
Okay.
Hey guys, today we are trying adaptive mind. I'm so excited.
All right, so that's one part of the stuff I was going to show you. Okay, the next one is let's come in.
Why do ships?
Let's check something else. I guess this is going to be good for us. Okay. Let's check this out again.
Archimedes Principle. We're all aware of the fact that some objects float in water while others sink. Let's look at a balloon. Do you know what makes a balloon float on water? Well, it's the upward force exerted by water that makes the balloon float. To experience this, try pushing the balloon underwater. You will feel an upward force that makes it difficult to push the balloon down. Now release the balloon, it bounces back to the surface. What happens here is that the applied force acts in the downward direction, pushing the balloon down, but the water exerts an upward force on the balloon, pushing it up. This upward force exerted by water on the balloon is known as upthrust or buoyancy, and the upward force is called the buoyant force. Have you ever wondered why an iron mail sinks while a huge iron ship floats on water? Let's see. The iron mail sinks as it is solid and compact with less volume in water, and its density is greater than water. Thus, the upthrust exerted by water on the nail is less than the weight of the nail. This causes it to sink. An iron ship floats as it is hollow, filled with air and occupies more volume in water, and its density is less than water. Thus, the upthrust exerted by water on the ship is greater than the weight of the ship, letting it float. These examples indicate that the magnitude of the buoyant force depends on the volume V of the immersed part of the body, the density ρ of the fluid, and the acceleration due to gravity G. Thus, upthrust of buoyant force is equal to V rho G. In general, an object experiences a loss of weight in water due to the upthrust, and it is equal to the weight of water displaced by it. are answered using the law of buoyancy, also known as the Archimedes Principle, named after the Greek scientist who discovered it. Archimedes' principle states that when an object is immersed in a liquid, the apparent loss of weight of an object is equal to the upthrust, and this is also equal to the weight of the liquid displaced. We see the uses of this principle in our daily lives. Ever caught a fish with a fishing line? When pulling the line, you would have felt the weight of the fish in water is lighter than when the fish has surfaced. Say the weight of the fish in water is 4 kilos. Its approximate weight outside would be 5 kilos. Well, the water level too has come down. This difference in the volume of water level will equal the loss in weight of the fish when in water. That is, the weight of the fish when outside minus its weight when immersed in water equals the loss in weight of the fish. So the loss in weight of the fish will equal the weight of the decreased water. This is because the upthrust of buoyant force is equal to the weight of the decreased amount of water. Thus, Archimedes' principle is verified. Certain technologies today work based on the Archimedes principle. To name a few, the designing of ships and submarines, hydrometer is used to find the specific gravity of liquid, and lactometers used to determine purity of milk. Things to remember. The upward force exerted by a fluid is called upthrust or buoyant force.
Please write this. The upward force exerted by fluid is called upthrust or buoyant force. Okay, have you written that?
Yes, sir.
Force. Upthrust or buoyant force equals V rho G.
Okay, the upthrust is equal to V density times density multiplied by your gravitational acceleration due to gravity.
Archimedes' principle states
Don't worry, don't
that
write
when
this
a
yet.
body is partially or fully immersed in a fluid, it experiences an upward force that is equal to the weight of the fluid displaced by it. Archimedes' principle is also known as the law of buoyancy.
Okay, I guess we are getting an understanding of what we have here.
last year.
I'm coming.
But I know.
Okay. Let's just check. I think I still have how many more to go.
Professor Dave, let's learn about fluids.
I'm coming.
A few days back, I read
Coming. Okay, let's see this. Let's see this also.
Say you have a beaker filled with water and you put your index finger inside it. You'll observe that the water level rises slightly. You put in 2 fingers, the water level rises a bit more. And now when you put in your hand up to the wrist level, you'll see that the water level increases significantly. The ancient Greek mathematician Archimedes observed something similar when he got into a bathtub. When he got in, he realized that the level of water went up. In both the cases, you notice that the water is displaced by the object that goes in. Keep this thought in mind. We'll come back to it soon. In our previous videos, we've seen that when an object is placed in or on the fluid exerts a buoyant force on it which acts upwards. The Archimedes principle goes just one step further in saying that the buoyant force applied by the fluid is equal to the weight of the displaced fluid. We can take a simple example to understand this. Take a 5 kg solid object and suspend it by a spring balance. The balance will read 5 kilograms. Let this be the first case. For the second case, take a beaker of water which has a small opening at the top. The water in the beaker right up to this point where the opening is. And we keep a small container under the opening. Now slowly lower the solid object into the water and you'll see that the reading will be lower number as compared to the previous case. Why is that? It's because of the buoyant force acting on the object. You would have also noticed that some water was displaced. Now in this context, we can say that the weight of this displaced water is equal to the magnitude of the buoyant force acting on the object. That's the Archimedes Principle. When an object is immersed
Okay.
fully or partially
I will need you to write this one. I think I prefer this one.
in a fluid, the upward force applied by the fluid on the object is the same as the weight of the fluid displaced by the object.
Please write this. This is Archimedes' principle now. When an object is fully or partially immersed in a fluid could be a liquid, it could also be a gas. A fluid could be a liquid, so put in brackets liquid or gas. Because when we say a solid cannot flow, but fluids can flow, gases can flow, liquids can flow. So when an object is immersed fully or partially in a fluid, liquid or gas, the upward force applied by the fluid on the object is the same as the weight of the fluid displaced by the object. Have you written that?
Okay.
Where is this principle applied? Can you think of examples? How do you think large steel ships float? It's simple. If the weight of water displaced by the vessel below the keel is equivalent to the vessel's weight, then everything above the keel will remain afloat. That's because the water too applies an upward buoyant force on the ship, which is same as the weight of the water displaced by it. There's just one important concept left in this section, and that's relative density, which
Okay. I guess with this now, you have a big knowledge now of Archimedes' principle, right?
Yes, sir.
Okay, I believe you have. I think there's one more I just wanted us to look at. Let's. Oh,
Hi, have
Tom,
you
what's this? What's this? What's this? Okay, so this. What did I do now?
Hi, I'm Brad Callen, and in this
Come,
video, I'm going to show you
please.
how anyone just
I think I was made.
to be known as fluid.
Okay,
So let's take this example of
I think.
I'm going to replace the word fluid with the word water in this statement. So now the statement becomes
Let's just check this out.
immersed fully in water. Upward force that is equal to the weight of the water displaced by it. Now let's cut this statement to two parts. The first part is when a body is immersed fully in water, it experiences an upward force. The second part is upward is equal to the weight of the water displaced by it. Let's understand the first part with a simple experiment. When a body is immersed fully in water, it experiences an upward force. And that's very easy to see because if I leave this ball, you can see it bobs up. Why? Because water is pushing it with an upward force. And this upward force is also known as upthrust or buoyant force. You can try it out yourselves at home. All you need is a bucket of water and a plastic ball like this. So when you hold the ball down like this, you can actually feel the upward force on your fingers. So I'm feeling the force here, and again when I leave the ball, the force brings the ball up. So how do we measure the amount of upward force? We know that an object feels
lighter when it's held in water as compared to air. Now, why is that? That's right, it's because of the upward force of water. So the difference of the weight in air and the weight when held in water will give us the amount of upward force. Let's go ahead and try it out. For this experiment, I've taken this hollow ball and I've filled it with coins here to make it heavy. Let's measure the weight of this ball, which is filled with coins, with the help of this spring balance. See what is the weight here. So as you can see, it is 500 grams. Or to be more precise in physics, the weight is 500 gram force. But for this video, we just keep things simple and use gram as the unit of weight. And this weight is known as the real weight of the ball because it is the weight in air. Now I'm going to immerse this ball into this liter of water and you carefully observe what is the reading of the spring balance. I'm going to lower the ball here. Weight of the ball when it's immersed in water. The ball is held in water. So why is that? It's because of the upward force of the water. And the weight in water is called apparent to lose weight. How much is this apparent loss in weight? Would be minus the apparent. 500 grams minus 300 grams. That's 200 grams. What will make it 200 grams? Note that the upward force is contributing to this. So the upward force is actually the loss of weight, which is 200 grams. Now let's take a look at the second part. So I'm going to go ahead and tilt this larger beaker. Smaller beaker. Let's try it one more time. Measure the weight of this water that has displaced. I'm going to pour this displaced water into the pan here. So what is the weight of the water? As you can see, it's 200 grams. So the upward force and the weight of the liquid displaced are both 200 grams or 200 gram force. So they are equal and Archimedes is correct. Now let's go back to our statement. When a body is immersed fully in water, it experiences an upward force that is equal to the weight of the water displaced by it. Archimedes' principle also works for the partially immersed case. So for the when I have this ball partially immersed in water, so the upward force, which is measured by the loss in weight here, is equal to the weight of this water displaced. Archimedes' principle works for both the cases, whether the object is completely immersed in water or partially immersed in water. And in fact, it works not only for water, but any liquid and gas. So we can say that this works for any fluid. So the statement becomes, when a body is fully or partially in a fluid, it experiences an upward force that is equal to the weight of the fluid displaced.
Okay. I guess you understand that better there now. Hello? Hello?
Yes, sir.
I guess you understood it better there, right?
Yes, sir.
Okay. So,
Yes, sir.
okay,
Is Archimedes
I guess it's not done.
on our concept board.
There was an advert coming up, so I had to stop it.
Upward force is equal to
I'm coming, please. Let's come back. Let's finalize that video.
the weight of the liquid displaced. We also saw in this video that the loss in weight of the body is equal to the real weight minus the apparent weight. And this loss in weight was used to measure upward force. Since upward force and loss in weight are equal. Remember, I promised a mnemonic at the beginning of this video to help you remember Archimedes' principle. So rather than upward force, you can remember it as upward force. Now let's split the word. So we have up equal to walled. So that is upward force is equal to the weight of the liquid displaced. I hope this mnemonic helps you remember the principle. Now, how is the upward force related to the volume of the liquid displaced? We've learned that the upward force is equal to the width.
Sorry. Oh no, shouldn't have done this. All right. Now, what we'll try to establish the facts. Okay, guess it's up now.
Weight of the liquid.
Let's wait for it.
And we know that weight is mass of the liquid, where T is the acceleration due to gravity. Now, what is the formula of mass? Volume to density. So we get that the upward force is V into G. But I like to write it as L, because it helps me remember that it's the volume and density of the liquid displaced and not the volume and density of the body. So let's go ahead and add this formula and the mnemonic to our board. Here's in summary what we've learned in this video so far. I highly recommend you to pause here. Now that we are done with Archimedes' principle, are you ready to move on to our top 3 questions on this topic? Here are the top 3 questions. I encourage you to pause here and try to solve them. I'll be posting the video.
Okay, can you try that? Did you get those? Did you get those? Let's look at the question. You said an object weighs 200. An object weighs 200 grams in air and 170 grams when completely immersed in a liquid. An object weighs 200 grams in air and 170 grams when completely immersed in a liquid. Number 1, calculate the loss in the weight of the object. Calculate the loss in the weight of the object. Number 2, calculate the buoyant force on the object. Calculate the buoyant force on the object. Okay, so can you do that? Have you forgotten that you did well in lots of weights? Have you forgotten that the upward force is the same thing as the weight displaced? The upward force is the buoyant force, which is also the same thing as the weight displaced.
Yes, sir.
Correct. So what will be the buoyant force now?
Vertical.
What will be? Are you still confused?
Yes.
Yeah, it will still be 30, but just convert it to newtons. because of the unit. I guess the unit was, maybe you were scared of the unit because it was in gram. It will still be 30, because buoyant force is the same thing with upward force. So it will still be 30, but you have to convert it to Newton.
Zero point 0.3 Newton.
Sorry?
0.3 Newton.
Okay. So are you sure of that?
Yes.
Okay. Okay. Remember, force is equals to MA. Remember, force is equals to MA. Okay.
Yes, sir.
Now, so it's still going to be, it will still be the same thing, but the thing we should understand is that buoyant force and up thrust are the same thing, and that would also be equal to the weight displaced, which is the loss of weight. All right. Now I'll give you an assignment. Give you an assignment to work with. Should be an assignment. Where is it? Okay, take this question. An object of density 15 gram per centimeter cube. An object of density 15 gram per centimeter cube weighs 100 gram. Weighs 100 gram when suspended with a string. When suspended with a string from a spring balance. It is then lowered into a liquid of density. It is then lowered into a liquid of density 0.9 gram per centimeter cube. It is then lowered into a liquid of density 0.9 gram per centimeter cube. Until two-thirds of its volume, is immersed in the liquid.
So this is 2/3 or 1/3?
Two-thirds, 2/3. Until two-thirds of its volume is immersed in the liquid. Calculate the tension. Calculate the tension in the string in Newton. Okay, I'm going to give you an idea of how to solve this. Calculate the tension in the string in Newton. The first thing you do is convert all those grams you are seeing there into kilogram. Convert those grams, like the gram per centimeter cube, convert it to kilogram per meter cube. That gram per centimeter cube, please convert it to kilogram per meter cube. The other one you're seeing 100 gram, also convert it. Now, once you've done that, the next thing is to get the volume of the object. Actually, density is equals to mass over volume. Density is equals to mass over volume. So if density is mass over volume, that means volume will be mass over density. Now, once we have gotten the volume of the object, now we are going to get the volume of the object immersed, because they said until 2/3 of its volume is immersed in the liquid. So that means we are going to get the volume of the object. Now, the volume of the object that has been immersed in water, that will be 2/3 multiplied by the volume of the object that we got before. After getting that, the next thing to do is to get the mass of the liquid displaced. The mass of the liquid displaced. The mass of the liquid displaced, which will be the volume of the object that was immersed multiplied by the volume of the liquid. Multiplied by the volume of the liquid, because we're giving the volume of the liquid to, I mean the density. Sorry, I said the mass of the liquid displaced is going to be the volume of the object that was in water multiplied by the density of the liquid. We have been given the density of the liquid to be 0.9. Okay. Now, after getting that, remember the mass will be in kilogram, not in gram. After getting that, we get the weight of the liquid. If you have gotten mass, it's very easy to get the weight. Just multiply by 10. That gives us the weight. Now, we know that upthrust is the same thing as the weight of the liquid displaced. The upthrust is the same thing as the weight of the liquid displaced. Now, the tension in the string that we're asked to find will become the weight of the object, which is the weight of the object minus minus the upthrust. The weight of the object, which is 1, weight of the object minus the upthrust. So that is how to do that. In our next class, we are going to be looking deeper into other calculations. We're going to go deeper into other calculations. Number 2 assignment is explain the principle of flotation. Explain the principle of flotation. Explain the principle of flotation. Okay. Yes, you're done with that, right? You're done, right?
Yes, sir.
Okay, let's pray, please. Any question from there?
No.
All right, let's pray. Father, we thank you for today. Thank you for how far you've helped us. Blessed be your holy name. Thank you for wisdom. Thank you for your strength. Thank you for speed. I pray for greater dimension of wisdom upon your daughter, understanding. In Jesus' name I pray. Hello, are you there?
Amen.